All right, let's talk about what happens when you smash two of the biggest frontiers in technology together: quantum computing and artificial intelligence. We're talking about a combination that could literally redefine what's possible.
You've probably seen the headlines, right? They make some pretty wild claims. So the big question we're going to try and answer here is this. Is quantum computing really about to give AI actual superpowers? Like something out of a movie? Let's dive in and unpack this. Okay, so first up, let's get into the dream. This is the big, exciting vision. This is where all the hype comes from, and it's what has researchers and, frankly, entire industries just buzzing.
So, what's the secret sauce here? Well, it comes down to this idea of superposition. You see, a normal computer bit is simple. It's a 0 or a 1. But a quantum bit, a qubit, it can be both a 0 and a 1 at the exact same time. The analogy here is perfect. Think of a classical AI in a maze. It has to go down each corridor one by one to find the exit. A quantum AI, though, it gets to explore a massive number of paths all at once. This isn't just about being a little faster. It's a completely different ballgame.
And look, this isn't just theory. A few years back, Google's quantum computer ran a physics simulation that was 13,000 times faster than the best classical supercomputer on the planet. I mean, that just shows you the raw, mind-bending potential we're dealing with. It's the kind of speed that could take a problem that would take centuries to solve and knock it out in a few minutes.
But all that power has a pretty serious dark side. One of the biggest worries is something called harvest now, decrypt later. Basically, bad actors are out there right now scooping up all our encrypted data and just saving it. They're playing the long game, waiting for a quantum computer that's powerful enough to use an algorithm called Shor's algorithm. And when that happens, boom, pretty much all of our current encryption becomes useless. We're talking decades of secrets, medical records, financial data, government intel, all laid bare.
Okay, so that's the incredible dream and the kind of terrifying nightmare. Now it's time for a reality check. Let's ground ourselves in what's actually happening today, because it's a much noisier, much more challenging picture.
Right now, we're living in what's known as the NISQ era. That stands for Noisy Intermediate Scale Quantum. And noisy is the key word here. Today's quantum computers are unbelievably fragile. The slightest vibration, the tiniest change in temperature, can throw off their calculations and create errors. One expert put it perfectly. He said we're in the 1950s vacuum tube era of quantum computing. The potential is obviously there, but the machines are just really finicky. And this really lays out the gap we're facing. The promise, the dream, is for these perfectly stable, fault-tolerant, logical qubits. But the reality? We have noisy, error-prone, physical qubits. We dream of a system that can hold its quantum state, but today that state collapses. It's called decoherence in just nanoseconds. So while we talk about breaking encryption, the truth is today's machines are nowhere near powerful or stable enough to crack something like RSA 2048. And when you look at machine learning specifically, the reality check gets even sharper. Researchers put current quantum machine learning algorithms head-to-head with some of the best classical AI models out there. And their conclusion was, well, pretty blunt. For now, QML just doesn't hold a candle to tools like XGBoots. The quantum advantage for AI? It just isn't here yet. And here are the huge roadblocks that engineers are working around the clock to solve. It's not just noise. There are these weird problems like barren plateaus, where a quantum AI model just stops learning as it gets more complex. Just building bigger, better machines is a monumental engineering challenge. And on top of all that, there's a major talent gap. We're going to need about 40,000 more quantum engineers over the next decade than we currently have. So if the dream is still way out there and the reality is this tough, what's the path forward? Well, that brings us to the really clever solution that's actually working today, the hybrid approach. This is maybe the most important thing to understand. We have to stop thinking about quantum computers replacing our laptops or the servers in a data center. That's not the goal. Instead, think of them as a highly specialized coprocessor. You know, like how your computer has a GPU specifically for handling graphics, a quantum computer is like that. An accelerator built to do one thing: solve the ridiculously hard parts of a problem that make classical computers just choke. And here's what that teamwork looks like. You start with your normal classical data. You encode it into a quantum state. Then you hand it off to the quantum processing unit, the QPU, to do its magic. You know, finding some super complex pattern that no other machine could see. But then it hands the work right back to a classical CPU or GPU to do all the heavy lifting and optimization. It's a true partnership playing to each other's strengths. And this isn't just a cool idea, it's what's actually driving the field forward. If you look at a decade of research in this space, almost all of it is focused on these hybrid methods. Things like variational quantum algorithms or quantum kernel methods. Fancy names, I know, but the core idea is the same. Use the quantum computer for the really, really hard part and let the classical computer handle the rest. This is where the real action is. Now, this hybrid world isn't just being built in university labs. There is a massive ecosystem of real companies, big names, building the actual tools and hardware to make all this a reality. Let's take a quick look at the toolbox that's already out there. So here's the cool part. You can actually start playing with this stuff today. You don't need a billion-dollar lab. You've got companies like IBM with Qiskit, Amazon with Bracket, Google with Circ. They've all built these software kits that let any developer write quantum code on their laptop and run it on a simulator or even on real quantum hardware through the cloud. The barrier to entry is just dropping like a rock. And the hardware is being built specifically for this hybrid model. NVIDIA, for example, is developing something called NVQLink. This isn't just a fancy cable, it's a super fast data bridge designed to let classical GPUs and QPUs talk to each other inside the same data center, almost like they're one machine. This is the kind of deep engineering that shows you this is a serious, long-term shift with billions of dollars behind it. Okay, so with all of this amazing progress, the question is, how long is this all going to take? It's really important to have a clear-eyed view of the timeline. Most experts see this happening in phases. Right now, and for the next couple of years, the big focus is on creating new types of encryption that can't be broken by quantum computers. Then, in the late 2020s, we'll start to see quantum machines tackle very specific problems in science and finance. It probably won't be until the 2030s that we even see early prototypes that could threaten today's encryption, and not until the 2040s or later that this stuff becomes mainstream. And that brings us to what might be the single best way to think about all of this. This quote from Harvard's Quantum Information Science Center just nails it. They say this isn't a single aha moment. It's more like a slow tectonic drift that's gradually but completely reshaping the entire world of computing right under our feet. And that drift, it's already happening. The question isn't if this technology will change our world anymore, it's how. From the way we protect our data to the very future of AI, this new landscape is going to affect every single one of us. The only question left is, are we ready for it?